All right, so today we're going to look at a couple of more physics laws that are going to help us understand respiration. The first of these laws is Dalton's law. And Dalton's law basically says if you take a gas that's made up of multiple elements, so for example, let's take gas AB. Hold on, I'm going to take it off, eraser. So we have gas AB here, okay, and P equals pressure. So if we have gas AB, two elements, and the pressure of that gas AB can be broken down into two separate numbers. So the pressure of the total gas is going to be equal to the pressure of gas A plus the pressure of gas B. So if we take this information and we look at the air that we breathe, the air that we breathe is not 100% oxygen. It's actually made up of different types of gases. So let's look at this. The first gas, the most abundant gas that we have, is nitrogen, which makes up 78.6% of our air. Okay, then we move down, and the next most concentrated is oxygen. Oxygen makes up 20.9% of our air. And then those of you who have hair that's susceptible to frizzing is going to feel the humidity. The humidity in the air is actually water. And water makes up 0.5% of what we breathe. And then finally, we breathe in and we utilize oxygen. But when we exhale carbon dioxide. So carbon dioxide is going to be that last gas. Hold on, it's CO2, not C2O. And that's 0.04, a really small amount. But still, it's involved, or it is a part of our air. So looking at Dalton's law, if we take Dalton's law, so this whole equals out to 100%. The pressure of the air that we breathe is equal to the pressure of nitrogen plus the pressure of oxygen plus the pressure of water plus the pressure of carbon dioxide. So then now that we know that the pressure of air, which is composed of 4 different types of gases, can be broken down into the pressure of each individual gas, or the sum of the pressure of each individual gas. Now, let's look at Henry's law. Henry's law is about the distribution of those gas particles, so specifically in fluid. So if we look and we take a beaker of blood, we look at this air, okay? We know that the air particles are going to be bouncing into each other. You know, they're going to bounce against the wall, they're going to bounce against each other. Some are going to bounce up and out, they're going to bounce into the wall, bounce into each other. But as well, you're going to have some that is going to bounce into the blood. And it's dependent on the concentration within the blood as to how long it stays there, because you'll also have some that are coming out of the blood. Over time, it'll balance out. So this is initial, where there's not a lot of air that's dissolved into the blood. Over time, it goes into a state of equilibrium. Okay, where it's balanced, much like diffusion and osmosis will do. You'll have the diffusion across a membrane that will balance into an equal amount. Well, eventually, over time, you'll create that same equilibrium between the gas in the air and the gas in the blood. So if we look at oxygen, that's exactly what's happening here. We have the initial state where you've got a higher concentration of oxygen in the air that over time will level out and equalize, and you'll have equal amounts of oxygen in the air and in the blood. So now we've looked at 4 different gas laws. We've looked at Henry's law, which tells us that air particles of gas or gas in the air will bounce into the water and then eventually create an equilibrium of what's in the water and what's in the air. We know that air, the pressure of air, can be broken into the sum of all its parts. Kind of like when you want to measure a pet and you don't have a pet scale at home. You go, you weigh yourself, and then you step off the scale, and then you pick up your pet and you weigh yourself with your pet. And then in order to find out how much your pet weighs, you subtract your weight from the total weight, and that gives you the weight of the pet. Kind of like what Dalton's law is about. And then we know that gas likes to spread out and that there's an inverse relationship. So if there's an area of high pressure, the volume, where there's an area of large volume, the pressure is going to be lower. And where there's an area, or if a gas is being kept in a small volume or a low volume container, the pressure of that container is going to be higher. So there's that inverse law. And then we know that it likes to spread out. So let's look at how this applies to the blood. So this here is a diagram of the alveoli. And if we look here, we know that, let me make my brush smaller. We know that oxygen and carbon dioxide are moving across those membranes. Now, looking at Henry's law, we know that you will eventually have an equilibrium. Okay, if there's a high concentration, going back to the fact that the gases like to spread out, the gas will move into a direction of low concentration. That's what we see here. So when you are in the alveoli, you have got air, which has a higher concentration of oxygen than the blood does. So you'll see diffusion of oxygen go across those membranes and into the blood to attach to the hemoglobin to be brought to the tissues. Conversely, or on the other side of that, you have the air or the blood coming back from the tissues, which is carbon dioxide rich. So what you'll see that carbon dioxide move to the area of less pressure and more space to diffuse out of the blood. And that is basically how, in conjunction with pressure and concentration and volume, how you see the blood at the alveoli diffuse or transfer its gases across the membranes. To recap, you've got smaller volume equals higher pressure. That higher pressure, the carbon dioxide is going to want to get away, so it's going to diffuse out of the blood and into the alveoli to be expired into the air. And then as well with the oxygen has a higher concentration in the air than in the blood, so it will move down that concentration gradient into the blood and away off to the tissues it goes. And this is basically the long and the short of how we transfer gases at the site of the alveoli.